All right, good morning, everybody. We're going to kick off this morning by further enhancing our skills with linked lists. So, I want to review the linked list methods that we've been developing over the last couple of class periods. And then I'll introduce the next one we're going to work on today in preparation for our redemption opportunity on Wednesday, in which you will showcase how much you have learned about linked lists. So, just to review, the data structure itself is very simple. You have a value, which is a string, and then a pointer to another node. And that's all. In a way, that's confusing because it's a recursive data structure and you can easily lose track of where you are. And that's a lot of reason why we're doing this extra practice. So some interesting things we've done with this include setting up the constructor. And I think one thing we gained some appreciation of is the fact that even something as simple as the constructor is actually a really powerful idea and can be really useful in all kinds of ways. In particular, thinking strictly in terms of the constructor enabled us to create a method for creating a list from a string that was simpler overall. That is, by cleverly having the constructor point at some pre-existing node, than just by kind of creating more in isolation like we had to do in this version down here. So even the constructor can be a really powerful utility when building a linked list. And of course, that applies to lots of data structures. A well-formulated constructor is a powerful ally and tool. We developed a remove last method that scoots all the way to the end and sets the very last thing to be null. So all the way to the end means the thing after where I'm at is null. Go ahead and set that to null. And then if we're not at the end, we just recursively remove last until we get there. We then did its symmetric equivalent, adding to the end. So we created a new node at the very end once we got there. Otherwise, we recursively set the value down until we got there. Then on Friday, we did something that was maybe a little more sophisticated. Add a node after some value had occurred in the list. So it was very similar to adding to the end, except that we had to explicitly seek out a target value at that point. And then lose alternate nodes was the method from the exam. So what I would like you all to work on to kick off class today is the following. Let's call this remove after. So value after, yeah, we'll just have that. And so here's going to be the idea of remove after, is that you're going to go through this list, and when you find a node that has your target value, I'm going to rename this actually be target value. So when you find a node that matches your target value, you're going to remove the node after it. And if you never find it, you're not going to remove anything. So you're just going to get all the way to the end, and then you're just going to quit. So you're going to go through the list until you find your target value, and then you're going to remove the node after it. So take 5 minutes, see what you come up with, write it out on paper, and I will be developing a unit test for you in the meantime.
Can you scroll up to the place after or something?
To what?
To the place after function?
Not really, no. You should be able to do it from here.
Well,
yeah. pretending this is a test or practicing for a test. No questions. No. All right, do we have a volunteer ready to share their solution? A volunteer. Elijah.
I said if no dot
Next equals next dot next. Is that? Yep. Okay. All right. So one important caveat is we don't need to prefix value with anything like node. If you want to make the scope clear, you can say this dot value. But node dot value isn't going to quite get you what you want. Let's try it out. So I'm going to run node test. And I've got my brand new unit test right here. Test remove after. Okay, it did not work. So we're going to examine what happened and see if we can figure it out. So I have a null pointer exception on line 69. Would anybody care to guess why I have a null pointer exception here? Yeah, Paxton.
If your list is only one node, then your next is null and there is no next dot next.
That's right. Good. So
We said we would check the null value.
you're right. How might we do that, Morgan?
If next dot or whatever, value dot next dot equals node equals null, or, you know, I'm sorry, I'm trying to think of the best way to describe it.
Okay. You have a good intuition. The syntax, like you mentioned, is lacking to some degree. Anybody else? Good. And then what are we going to do, Elijah? If anything. Nothing would actually work fine. And now, with this little caveat added, Elijah's solution works perfectly. Now, admittedly, this is some very strange looking code with this gap. So here's a way to reformulate it to maybe make it look a little less odd. We can say if next is not equal to null, at that point, this other if else is only considered in that case. So let me go ahead and run this. Yeah, it works perfectly fine. So let's walk through this and make sure everybody is clear about how this works. If next is equal to null, we're at the end and there is no after to be removed. So we're done. There's no work to be done. So the only case where there's work to be done is if next is not equal to null. So in that case, if our value is equal to our target value, we say next is the thing after next. And we know that this is going to be a valid reference, next.next, because next is not equal to null. This if statement here enables us to prove that this is a valid reference. Otherwise, we just keep looking. So, any questions on this method? So for the next one we're going to work on, it's going to be similar, but with a subtle difference that causes us to have to rethink things a bit. We are just going to call this remove value. Okay, but this one is tricky, and I want you to see why it's tricky before we start creating it. Let's say I have this linked list, A, B, C, and I want to remove A. So I'm given, my this node, so to speak, is A, or thought about in an alternative way, at some point there's some reference that's live for this node. Maybe we'll call the variable N. I want to remove A. Why is this tricky compared to remove after? Yeah, Elijah.
You have nothing to say your order off of, like since A is the first one, you can't say like as this one to the next one behind this one instead of the pointer to the next.
So you're right. So Elijah's right about that. We don't have any way to remove it, because if we just kind of get rid of it, N isn't pointing at anything. So what we wind up having to do is add a return value signifying the node which ought to start the list. Let me show you what that means in code terms. I can't just return void. I actually have to return a node which corresponds to what the start of the list ought to be after this happens. Another way to think about this is if we look over at node test, I want you to look at my test remove after. I have no scenarios where I deleted A because there's no way to even talk about it because A isn't after anything. So now here is what I have in mind for this remove value. Let me write out the unit test. So let's say I create node L1 equals node.create from ABC. And now I want to say L1.remove value A. Well, what I'm really going to need is to say that L1 equals whatever the new start of my list is. And then I can put in my assertion. I can say assert equals BC, comma, L1 dot toString. And so that's a unit test that I formulated that takes into account that the first node might have changed. So, bearing that in mind, in the next 5 minutes, create a solution for remove value. The return value of which is a node that represents the new start of the list, if necessary. Well, you'll always be returning something, Sometimes the old start will still be the new start.
Okay, so remove value is supposed to remove the node that you're supposed to start from.
Just removes the value from anywhere in the list, including the start. All right, anybody ready to share a solution?
I mean, my thought was just to do value dot, whatever the value is equals next. Which I know that may not be the correct solution, but if that's the case, because all you're doing is whatever.
So stop there. His suggestion is to set value to be next. Why is this not a correct solution? Yeah, Tate.
Next is a node.
That's correct. That's a type error.
Well, whatever the string, whatever the correct name for the query.
But you have to make a node go away. You can't just reset the names.
I mean,
Anybody else got a solution? Paxton, what do you have?
Something not finished, but what
Let's-
I have written down so far
Mhm.
is I started it with if next is not equal null,
Okay.
then if, and we said we're calling the top node n, right?
You don't know about n here.
Okay.
Everything has to be in terms of the node you're within. But you need to be ready to think about what it means that there's some n pointing at it.
Okay, I need to rethink this.
Okay, that's fine. So let's back up. Anybody else willing to volunteer? Or am I going to call on somebody?
I mean,
Colin, or Caleb, what do you have? Okay. Okay. This dot next dot value dot equals target value. Uh-huh. Okay. Turn this. Okay.
And then I just had.
Okay. So this is something to work with. It's not a correct solution. And in particular, this solution doesn't really take into account the idea that you're removing the current node. Right? So imagine you're at the very start. This doesn't really remove it. So what I actually want us to do is back off from the idea of looking ahead. We need to think about where we are. Okay? So if we're thinking about where we are, we can take this if statement and edit it to think about where we are. So if this dot value equals target value, then there's a thing that we need to do. Otherwise, we're going to do a different thing. Structurally, that's correct. And I wanted to highlight the fact that Caleb got that right. But the condition needed to be just a little different. Now, given that the condition is different, the interior is also going to be different. If the node we are at matches the current value, what should we return?
The next node, that's what.
The next node, because that's really where it's going to start. At that point, we just return next. Now, note that in the else, we are receiving a pointer back, right? When we call next.remove value target value. So again, something I want to highlight that Caleb got right here is this is a good recursive call. Now, admittedly, is there any circumstance where this recursive call won't work? If there's only one thing, and how do we detect that? Next is null, right? So if next is null, what do we return? Well, if we're not deleting this, we can return this. Good. Now let's say next isn't null.
question, could we short?
We could.
You know, it just be,
More aligned. Sure, we can do that. But now we've got the interesting question. What do we do in this case? We're getting a value back. We're getting a value back. What do we do with the value we're getting back? And what does the value we're getting back represent? The top of what list? You have a good idea there. It's the top of something. That's good. What is that thing that we're getting back? The thing we're getting back is the remainder of the list with the value removed. So what do we do with that remainder of the list with the value removed? We do this. All we have to do is set our next to be whatever list we get back after removing the value. This may seem a little silly because you wind up resetting the next pointers usually to just the same node that they were. But at that one time you don't, that's how you actually affect the removal from the list. And in this case, what do we return? We just return this. We return ourselves. And then that sort of looks redundant. So I'm actually going to refactor this back with the else the way we had it originally. What we can say is if next is not equal to null, what we're going to do is say that next equals next.remove value. If next is equal to null, there's no need for any recursion because there's nothing left. And then in either case, we will return this. Let's try it out. And it works perfectly. It works perfectly. An exercise for you to try at home, we don't have time to do it in class today, that uses this idea is insert before. Insert before also needs this concept. Because if you insert before, you might be putting something before the current start of the list. Okay? Any last questions on this one before we talk more about heaps? Let's talk more about heaps. So last time, we talked about the idea of a priority queue and the notion that we could build it using kind of a tree structure. And the idea of the tree structure is that initially at the beginning of time, we just have some value that's at the top. Then every time we add a value, it goes towards the end of the tree. So say we put in a 7, and then we observe, 7 is bigger than 5, so we actually need to reverse them. And so 7 is now at the top of the heap, and then 5 is down here. And let's say we put in a 3, and now we put in a 6. Well, 6 and 5 need to be swapped. But now 6 is less than 7, and so life is good. So an interesting question arises, though, about how exactly do we implement this? What is the underlying data structure that can store this heap information? The answer is that the easiest way to do this is actually with an array. Here's the concept of our array. I am actually going to show what this heap looks like in the array as we also build its tree representation. So we'll start where we started before with the number 5. So initially the number 5 just goes at the start of my array. No problem, very straightforward. Now I put in a 7, and I see the 7 is bigger than the 5, and so I have to swap them. So the 7 goes here and the 5 goes here. Now in array terms, what happens is I put the 7 here, and now I see, oh, it's out of order relative to its parent, so I have to swap them. And this brings out a really interesting question, which is, for a given array element, based on its index, how might we identify the parent? Let's look again. I'm going to put a 9 here now. So 9's parent is 7, and they need to be swapped. So what I'm going to erase here, and then I'll erase in here, and then I'm going to fix everything. Like so. On the other hand, if I put a 6 in, whoops, that was excessively scribbly. So if I add a 6, who is its parent? The 5 is its parent, right? So we're going to erase. And now 6 goes here, and 5 goes here. So let's think about these array indices and see if we can come up with a formula for determining, based on the index, whose parent is whose. That's index 0, 1, 2, and 3. So we're not going to worry about parent of 0 because index 0 is the top of the heap. It has no parent. It is Adam and Eve, so to speak. Okay. So it gets interesting at P of 1. So what's P of 1? 0. Good. What's P of 2? Still 0. What's P of 3? Okay. Looking ahead, what's P of 4? Also 1. Good. Note that every parent has exactly 2 children, and so each consecutive pair of children shares a parent. And so, looking just ever so slightly ahead, what do you expect P of 5 to be? 3, 2. So P of 5 is 2. So see, 0 has its children 1 and 2. 1 has its children 3 and 4. 2 then has its children 5 and 6. Oh, the parent, it's the whoever the yeah. So based on these examples, can we come up with a general formula? What is P of I for all I strictly greater than 0? P of I, and this formula should work for all I strictly greater than 0. What's a general formula we can come up with? Let's think about some intuitions behind the general formula. Loosely speaking, what kind of operation should this involve? Division? Okay. Yeah, division seems to make sense. Why does division make sense to you?
Constant ratio less than the element you're at.
Indeed. And what is that constant ratio like? What's its feel?
The second one is divided by 2.
We're dividing by 2 and subtracting 1. We are doing both things. The question is, in what order are we doing the things? Do we subtract 1 and then divide by 2, or do we divide by 2 and then subtract 1? You could. Let's see if we can get away with one function that works for both even and odd. What would that look like? And we know it involves subtracting 1 and dividing by 2. So they're both things we're doing to I. Right? Let's consider both candidates and see what works, right? So if I have, so here one candidate would be I minus 1 over 2. The other candidate is I over 2 minus 1. Let's apply P of 1 to both situations. What's 1 minus 1? What's 0 divided by 2? So for P of 1, this works. What is 1 divided by 2? It'll be round down to 0. We're going to do integer division because we don't have a notion of a fractional index, right? What's 0 minus 1? So does that work for P1? It's kind of a disaster, yeah. Let's try 2. What's 2 minus 1? Good. What's 1 divided by 2? Yeah, that looks pretty good, yeah. Well, let's try 3. What's 3 minus 1? What's 2 divided by 2? Hey, not bad. Let's try 4. What's 4 minus 1? What's 3 divided by 2? It's just 1. This is our formula. So the parent of a node at a given index, we can find by subtracting 1 from the index and dividing by 2. Of course, we also need to be able to find the children of a parent for when we're removing from the heap. So we have the left child of I, and we have the right child of I. These are going to have to be different functions. To determine them, we can invert the parent function and see what we come up with. Why don't we start with left? So we know that P of I equals I minus 1 over 2. And so in effect, we need to find I, right? So we're going to get I minus 1 equals 2P of I equals 2P of I plus 1. So really just did some algebra there. So this should reliably be the left child of I. Let's plug in some values just to sanity check things, right? If I is 0, what do I get? Yeah. So, I meant if P of I is 0, right? So if P of I is 0, I get 1. If P of I is 1, what do I get? 3. So coming back here, the parent is 1, the left child is 3. That's pretty good. How about if P of I is 2? I get 5. And sure enough, P of 5 is 2. So this looks like a pretty good formula. And so given that I've got a formula for the parent of I, and given that I've got a formula for the left of I, how might I get the right of I? Yeah, Paxton.
Should we just undo the other formula that didn't work for finding?
I'm not real comfortable with that. Yeah, and the reason I'm not comfortable with it is because we're not actually using that formula. Should we do something in terms of this formula, or might we even consider doing something in terms of this formula? What do you all think? Yeah, let's say we worked in terms of the left. What's the index of the right child if we know the left child? What's that, Elijah? It's just one bigger, right? So see, the right of I is just the left, dang it, sorry. The left of I plus 1. That's all it is. So let's rewrite these more concisely for your use, because after all, by tomorrow, off your phone, please. By tomorrow, you will be coding these. So, you know, it's nice to have them concise, right? So the parent of I is going to be I minus 1 over 2. Left of I is going to be 2I plus 1. And the right of I is going to be the left of I plus 1, or 2I plus 2. And that's how we can navigate through the heap. So note that in this scheme, a heap is an example of what's called a complete tree. That is, there aren't going to be any empty children anywhere. The entire tree will be filled in.
Wait, at the end of the right I, is that a minus 2I plus 2?
No, that's an equal sign, but that was an understandable confusion. Yeah.
Yeah, I couldn't tell.
Yeah. Yeah, my top equals was just kind of the dot. Yeah. Good. So there are 3 operations we're going to do on a heap, just like we did on a queue or a stack, right? We're going to need to peek. And this is really, really easy. We just return array bracket 0. Whatever is on the top of the heap is the value that we're expecting will come out. When we add some value, here it gets kind of subtle. And so, by the way, it'll be fine if you use like an array list for this, because then you don't have to worry about the resizing and so forth. You can let the array list take care of that for you. Okay. At this point, I feel like you have earned resized arrays.
So array lists can resize themselves.
Yeah, exactly. Array lists are resizing arrays.
Okay.
Yeah. So what's the sequence of events here? You're going to add v to the end of the array. And now what you're going to need is a while loop, right? And the idea is you're going to loop as long as we are out of order. So you're going to need a variable to track the index of v, and you'll need to set that up, before your loop begins, and you'll be making use of that index in your loop condition. So while it's out of order, and of course while you're at it, your condition might also incorporate some discussion of whether or not you've made it to the top. Because once you're at the top, you're in order by definition, okay? So while you're out of order and not at the top. Again, this is just a general concept. Turning this into code is going to be your job tomorrow, okay? So while you're out of order and you're not at the top, you're going to swap and then update your index. And that's generally what it takes to perform an add in a heap. You just stick it on the end, and then you kind of let it float up to the top.
It's like doing density almost.
Yeah, kind of, if it works for you.
Yeah.
Okay.
It's a way of seeing it.
Now we've got the idea of remove. And of course, remove is going to return whatever the current highest priority value is. So here's typically how we might approach remove. Remove is trickier than add, okay? And it's trickier than add because you've got choices to make. As you're removing, you're going to have to make a decision the way you didn't when you were adding. So how is this typically done? We will remove the last value and put at the start. So you're going to remove from the very end of your array. And well, before you do this, you're going to copy the value from the start of the array into some temporary variable. Okay, that's going to be what you return. Then you're going to take the value from the very end of the array, remove it, and store it in that starting location. It's going to come all the way around, and now you are guaranteed a crisis because that value is going to be less than at least one of its children. So again, you're going to have a while loop. So while you are out of order and not at the bottom, right? What you're going to need to do is pick the largest of parent, left, and right. Now, if the largest is the parent, that's great. You're done. But you'll actually have to have slightly different cases for the left and the right. So then what you'll do is swap with the parent, and then you're going to continue floating down the heap and fixing things up as you go. And that's remove. And then, of course, when you're done, you'll return your temporary variable that stored the value that was initially at the start. And that's remove. So this is really the heart of your lab this week, is getting the heap working.
So we're just going to be practicing putting this together.
But it'll be in a context, specifically the maze. And how the heap helps with the maze, I will talk about at the start of lab tomorrow. Because today, we're out of time. See you then. Yeah, Elijah.
Is there any way you could record the beginning of the lab?
Oh, yeah. Good point. I'll work on that. I'll make that happen.